All right, yeah, let's get started. Let's see where I left off. Full screen. Okay, so what did I do? Skip it. You know, let me just do that command again. Get F. Okay, so basically the whole point is to add the negamax function, and then like this heuristic is to do, and then incorporating it. So one thing I think that's kind of like a good idea right now actually is to actually move this to BumperCoins bot like I mentioned last stream. So let's just actually do that. Actually, let's cd into that status. Git log, latest temp, whatever. Okay, you know what? Git status. Let's just do a git add all. And then git, or yes, git status, git commit, save, like, yeah, it's temp, save waits, status. Okay, good. So now we're clean. Perfect. Let's go back there, git status. So what I want to do now is actually, let's open up the, let's obviously do a git restore of the, clear off the weights changes. Because we already have the weights that I committed in the other repo. Status. Okay, so now let's actually open this file up and kind of change, like kind of, so what we want to do now is we want to go to BumperCoins bot. And like you see how we have like mcts.ts and stuff, we kind of want to do something similar, right? So let's call this like AlphaBeta.ts. It's like that. You know, for good measure, I'm going to I'm also going to open up BumperCoins, the mcts.ts, or sorry, BumperCoins bot, mcts.ts, and maybe net.ts too, actually. Let's actually do that as well. Okay, so I think that looks good. Okay, so here's negamax. So let's just take everything we did right here, and let's just kind of copy it over, right? Delete that, and just paste it here, just like that. Okay, great. So now we have this. Now obviously the import statements are kind of off. Like there'll be a whole bunch, like instead of bot game state, let's just make it a game state. So like, okay, so depth, let's add some spacing, some space for imports. Okay, okay, so now we basically kind of have the changes. So we have, so let's just review this negamax stuff, right? This is before AlphaBeta. Let's just refresh. Number pos infinity, negative infinity. What's define? What? Okay. Negamax. Okay. Yeah, first we're gonna do this, then we're gonna do the AlphaBeta stuff, but this is just the base algorithm. Yeah, this makes sense. Okay, so let's see. So we have the game state, we have the depth, right? Now here the root call is like the depth, and then the color. I mean the like 1 for player 1, the -1 for the opponent, player 2. But like in our case, the node itself is the game state, and it has like the isP1 turn parameter. It's baked into the game state, so we don't have to pass it as a separate argument. So that's nice. It's bundled together. So then we get, so first of all we have to import the game state. So let's kind of like go here, copy that line, and we import the game state. Okay, so far we're good. Negamax, game state, and then depth. And this bot move, okay, so this bot move is stupid. We have to make it just a move. Great, well let's do that. And then let's import the move. So now we have a move also. So we have negamax takes in game state depth, returns the number, and it returns the move to play. Great. So this P1 turn is bot. So again, the game state. So it's P1 turn, and then if the well, let's actually make this a search command. Let's just make a substitution. Yes. 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 I approve of the change. I'm saying yes to that. Heuristic of the game state. Yes. Game state.clone. Yes. And then bot game state. Let's make it a game state. Great. Perfect. And let's do the same exact thing, but instead of this thing, let's kind of make that like this thing, the capital, like the type versions of everything. So child game state, child game state, child game state, child game state, child game state value. Okay, great. So I think a lot of substitutions are done. So back to where we were. So negamax, first we extract his turn it is. Then if the game is ended, that is a terminal state, then we have two outcomes. Either it's a draw or it's decisive. If it's a draw, we just return 0, and then there is no kind of move to play from here because the game's ended, so undefined. That's fine. And now if it's decisive, then we kind of figure out who won. So we can kind of encapsulate that information in P1 won, which is true if and only if player 1 has won. So then if the player won, if the person who won aligns with if the person whose turn it is won, then we return positive infinity, which is like, yes, this person really won. Because recall that this function, like this is not like what we did at MCTS. Like what we're returning is the evaluation of the game state from the perspective of whose turn it is, right? It's not the negative, it's not from the perspective of our opponents, right? So it's not whose turn it isn't. So there's a bit of a difference there. Again, like we take that into account by this -1, so that's kind of what happens. But yeah, that's a little subtlety. So then so again, so like positive infinity if we have won, because like it's the game states is player, like if the person whose game state it is, the person whose turn it is has just won, then it's positive infinity from their perspective, or else it is negative infinity. And since it's terminal, there's again no move to make. And if the depth is 0, then we just kind of, that's the point where we're saying, hey, like, you know what? Depth is exponential. So like we can only dig so deep. And once we cross like a certain depth, we're just going to refuse to consider any more rollouts, any more expansions. We're not going to explore any more subtrees. We're just going to accept that, like, we're just going to return the heuristic as our value. Again, the heuristic returns it from the perspective whose turn it is. That's in this comment right here. So we return the heuristic, and again, since we've kind of like hit like, I'm going to call this a pseudo-terminal state. Like, it's not like a leaf node in terms of the graph because the game's not over, but we're not going to explore any further. So from our exploration graph, like our recursive, if you kind of graph out the recursive calls, like this is basically a terminal or a leaf node from the perspective of the recursion. So like, we're going to say like, again, like, hey, like we reached the state, we have exhausted lots of depth to get here, and we don't want to explore anymore. We're not going to consider any more moves from here. So then the move that we choose is again undefined. So that's kind of fair enough. Similar logic as the previous one. Some notion if leaves are terminal, or like just the notion if we're not going to go any further. So now that we're here, we are going to dig a bit deeper. We're going to kind of recursively call on our children. So like there is some recursion going on. So we do want to return a move. Hence, we have like best move here. Okay, so then any type parameters? Just game state. Yeah, wait, bot game status. Let's make that a game status. Oh, actually, let me make the same substitution, right? From the bot game state to bot game status, then game state to game status. So change that, and that's it. Okay, great. So I think so far everything is good. So then the max value, again, is negative infinity, because like this max value is basically kind of like the, I guess you'd call that the alpha, right? In this case, like it's kind of like the value we're assured of. Like we can only look for better. Like it's like max value is again like we're just maxing over all the like we're just maxing like kind of like we're just like kind of looking at our children and kind of seeing which one is the best for us, and we just kind of return the move that produces that. So the best move is the move that gives us the max value. So to generate, yeah, we have to do this. This is an empty list right now, so we have to do. In fact, to implement this, let's add another to here. This, great. So then we have like a list of moves, and then for each move we kind of, so like, okay, let's just kind of go to next child. Like let's look at clone, search for clone here. So like kind of like here when we're kind of like doing apply move here. So whenever we do apply move, like whenever we call apply move, first we do is we take our game state and we clone it, and then we apply the move to the thing that we clone. Because apply move, again, as I said for the 1,000th time, is a destructive operation. Wait, am I streaming this? Yep, I'm streaming this. My mouse is going in circles. Great. Okay, that's good. Wait, oh, what's the screenshot? It's from the neural net. Yeah, it's the neural net architecture. Okay, so then next game state dot clone, and then we apply the move. So first we clone, then we apply the move. So then, and we also pass in, I guess, the previous one. But right now we're passing in just undefined because our heuristic, let's just say, is not going to use the velocity. I mean, it doesn't need prior. I mean, sorry, what am I saying? It doesn't need previous game state because it can just use velocity, right? I mean, I don't know. Let's just keep it simple and just do undefined. Just work on one game state at a time. So we clone it, and then we apply the move to it. So now we have kind of, we're working with the child game state, and again, we have not mutated the actual game state, so everything is fixed, everything is good to go there. Then value from our perspective, child game state value is we recursively call it on the child game state in the rest of the depth. But again, remember that the value we get from this, again, it gives you a value to move, right? We only care about the value for the purpose of recursion. And the value we get is from the perspective of the child. Therefore, we have to -1. We have to negate it, right? That's the whole negamax. That's what makes it negamax. And then, so now we get the value. And this value, again, from our perspective now, because we flipped it. So now if the game state value is greater than the max value, and again, it's going to be always true in the beginning because we set it as infinity, then we get some value, and and if we have kind of like discovered like a new better path that beats what we've seen so far, then we set it to our max value, and then we also note down the move that produced that, and I set equals to because I don't know, why not? I just said because what if we get some? Never mind. What if everything gives us negative infinity? Then like we want to return a move if we can. Return the best move, and then we return max move and best move. So that's basically that seems reasonable to me. I basically kind of copied the Wikipedia article, I believe. So but yeah, it makes sense. So this looks good. And then now, do we have any compile issues? Let's quit everything. Actually, let's just discard everything here. Actually, let me first CD into that one. Get status. Because we have kind of added AlphaBeta. Let's just do our good old-fashioned TSC command. Instead of this.train.ts, let's just do it on our AlphaBeta.ts. Okay, so there are some errors. But at least we copied it, so let's CD back. Get status. Get restore all. Status. Great, so now we're fresh with prod. Origin, remote, whatever. See that? Get status. Now let's look back at our errors. Have to import game status. AlphaBeta.ts, mcts.ts, and net.ts. I believe those were the files I'm considering. So the issue we had was, let's just run it again. Okay, game status. Copy that. Copy the game status. And then some bot stuff. Like, it's like bot status or something. Wait, oh, I already did that. Okay, never mind. Okay, so then bot move. Bot move. Let's import move. Oh, I already have the move imported. I'm pretty annoyed right now. Okay, great. So it compiles. So basically, all the work we did last stream, we just poured to BumperCoins bot, and then let's actually kind of look at the usage. So let's kind of go back to let's CP the actually, yeah, just let's CP over the alpha or BumperCoins bot AlphaBeta.ts into front-end client BumperCoins bot. Okay, great. So then status. Now we just kind of like have a new AlphaBeta.ts. So like if you kind of like go into like, so now let's let us actually use it in BumperCoins. So then be front-end client bot worker, something like that. .ts. Front-end client BumperCoins beta.ts. Okay, so now, okay, so then I have to kind of redo everything here. So you have the game state. Okay, let's just kind of take everything that we did in the past, and let's just kind of put that as a comment. Okay, so now what we're gonna do is kind of copy this, so we get the game state. And again, this thing, and then we convert it to a bot. Just kind of go here first. It's gonna copy this line here, but instead of that, we want to copy the function negamax. And then this will be from what? From BumperCoins dot, and then this would be from AlphaBeta. Maybe I'll change the name from negamax to AlphaBeta. Like maybe once we implement that. For now, leave it as negamax. So I have to remember to propagate that. I mean, compilers will tell us that. So negamax, we have negamax from there, and then we have the game state bot, and then let's just set the depth to and again, this depth will be users will get to adjust this depth. For now, again, let's just have the depth be equal to 3. A player, select this from an optional drop down menu, just like we have in Connect 4. We can toggle the BumperCoin, the number of MCTS simulations. We're going to let them toggle the depth. And then what we're going to do is we're going to kind of, let's look at the constructor here again. Function negamax takes in the game state. and a move. So what we want to do here, we'll kind of copy this right there. We want to let the bot move equal to the negamax. The negamax of the game state bot, and then the depth. And then what does it return? It returns a pair of the number and then the move. So we need the move, but it could be undefined, so we have to cast it as a move. So we return the second one, the move, as bot move this time. And then we do the same thing that we did there. We just convert it back and we post it. Status, get at all. And then PS, okay. Oh, we have to export it. Okay. Actually, you know what I'm gonna do? Oh, sorry about that. Let's actually call this AlphaBeta. Let's kind of, we have to export that. And where do we recurse on it? Just here. Okay, great. So now what we're gonna do is CP a fresh copy, and then we're going to kind of do this export function AlphaBeta, and then we're gonna call it right here, right there, and then the import too. Okay, so now hopefully, like, if we don't break any signatures, the contract we have AlphaBeta signature, then we just BumperCoin should just work, and then we can just do all our work in BumperCoins bot, and then we get it for free. I'll just CP it over the latest copy. Great. Status, PS. Okay, good. There's no node processes. Let's just kind of do the run.sh on it. It's doing something. Okay, great. It did it. It compiled. Let's kill all node. Okay, great. So now BumperCoins compiles, and now the remainder of our work can be happily done on BumperCoins bot repo. Yep, great. Status, get diff, and then get at all. We change the name from negamax to AlphaBeta. Status. Okay, great. So now let's just do like, okay, get log. Let's see where we are. So we just kind of did a bunch of weight changes. Declare, get status, get diff staged. Okay, so I think this should work as long as our heuristic works, and then we need to generate the moves too. So as long as we do the to-dos, we should have something that works. So then it's time to actually do AlphaBeta pruning on it. So let's just kind of, or maybe I should take a break and end the stream, and then hey, it's pi 3.14. I averaged 11 hours per day. Acceptable, but anyways, a bit excessive, but yeah, 314. So then what do we have to do now? So I'm thinking, like, before doing the to-dos again, I'm just going to review AlphaBeta and actually kind of add AlphaBeta in our that's where the negative, the positive number dot whatever those infinities were will come into play. Positive infinity, negative infinity, we set them for AlphaBeta, and then we just yeah, we just kind of implement them. In fact, yeah, I think that would be a good start. We just yeah. Okay, alpha beta. Let's just implement that first, and then do the to-dos. Maybe today I'm feeling a bit tired. It's really warm, really hot in Fremont. I think I'll just kind of do that. Maybe. Well, I don't think I'll do these two to-dos right now. But again, we can kind of use net.ts, like, again from, well, this changes to just the current directory. But yeah, let's talk about alpha beta then, right? Really straightforward stuff. Really straightforward stuff. Okay, this is Negamax, alpha beta. Okay, let's go back to the beginning, or a core idea. Okay, this is the crucial thing right here. This is the very crucial part. The algorithm maintains two values, alpha and beta, which respectively represent the minimum score that the maximizing player is assured of, and the maximum score that the same thing, they're flipped version of it. But from Negamax, we can consider it basically like the current, like the alpha is just like the best score that we are assured of, and then beta is from the other guy's perspective, like it's the one that they're assured of. Initially, alpha is negative infinity and beta is positive infinity. Yeah, worst possible. It's like the max value basically, which we're talking about. Then whenever the maximum score the minimizing player, whenever the maximum score that the minimizing player is assured of becomes less than the minimums. Okay, this is a bit confusing. Whenever the maximum score that the minimizing player, the beta player, is assured of becomes less than the minimum score that the maximizing player is assured of. Okay, well, what does that mean? Whenever the maximum score of the minimizing player, why is the max? Shouldn't it be the minimum? The whole point of minimum player is to minimize the scores, right? When the maximum score that the minimizing player is assured of means that like it's the best they can do. So I think it's like the minimum score, but like from the perspective of them, the maximum score is the minimum because scores are always from the perspective of P1 in this non-nega maxed idea. Then is assured of becomes, okay, fine, whatever the best that the minimizing player can do becomes less than the minimum score that the max, whatever the best that the minimizing player can do becomes less than the minimum score that the maximizing player is assured of. That is, in other words, beta is less than alpha. Okay, I don't want to read this. I mean, well, I just read it, kind of, but we break. But, so the minimizing player, let's just give some concrete numbers. So the minimizing player, let's just say, is assured of, like, let's just say, like, -5. That's, like, they're kind of assured of that. -5 becomes less than the minimizing score that the maximizing player is assured of. So the maximizing player, let's say that it found a line, a certain move, like the maximizing player, like the minimizing player, like it's like somewhere, it could be its parent's node or it could be some ancestor, it doesn't matter. But at some point, like, yeah, let's just pretend it's the direct ancestor. Actually, no, it is the ancestor, right? It's the one that passed it in. Because everything else is baked into that, like just by just by the propagation of alphas and betas that kind of go propagate down the trajectory. So then, like, okay, so then the alpha player, the maximizing player, let's just say that, like, the alpha, like, let's just say that before we, okay, let's just say that, let's actually draw this out. 1 minute left. Okay, so let's just say that, yeah, I like this idea. Let's just kind of like do that same thing. 1, 2, 3. And let's just say that, like, right here, after exploring this node, like, we considered everything. Let's just say that everything is the same, just for clarity. Let's just put these numbers in the perspective of player 1 only. Let's just say that we got, like, let's just say that we get like everything going to be the same, like 1, 1, 1, right? So this thing is going to kind of return 1. And then here we kind of have 1 as our best, right? Like 1 is like kind of, I think that we're going to call that the alpha, right? Maybe, whatever. Like we know that like we're maximizing over that. So like we know that we can at least do 1, right? First it was negative infinity, I believe, and then we can at least do 1. And now let's say that we consider this. Like if we do, like in 1 is, let's just say the range is like -1 to 1 or something, like a 10H, or not. Yeah, let's just pretend it's -1 to 1. So basically like this one is like -1 and negamax from that perspective, but let's just do everything in player 1's perspective, all the values. Because again, we're not doing negamax yet. I mean, we're just focusing on the Wikipedia article and trying to understand it from the context of like just the whole alpha beta pruning concept, just for me to refresh it. So okay, so this maximizing player, he's assured of at least, he or she is assured of at least getting the score of 1, which is really good. Or let's just say, well, no, let's just say like negative, let's just not specify a range. It's just 1, whatever that means. We don't know the significance of 1. We just know the only significance of A is less than B, then the score of A is worse than B. That's it. We just know like it's the order of numbers. We don't know anything else. Like we don't know what the magnitude represents yet. We don't care. That's beside the point. We just strictly concerned about equalities and inequalities. So now we've considered move 1. So by taking this path, we know we can at least get 1. So now we're looking at 2. So this is the minimizing player. Let's say that the minimizing player like goes here and then sees like 0.5, right? So now we can basically, like if we kind of look in alpha beta, right? The maximum score of minimizing players is assured of. And again, this actually, like this line kind of annoys me because I feel like it's like the best they can do, and their objective is a minimizing. So it's like, it's more like the minimum score, but like from the perspective of them, it becomes a maximum, whole nega switching thing. So if this one becomes less than the minimum score that the maximizing player is assured of, right? Maximizing player need not consider any, like, can stop kind of, the minimizing player can say, you know what, let's just stop exploring because these moves, again, will never be reached in actual play. Yeah, okay, that makes sense, but let me just show it, right? So now, like, we saw 1.5, right? So whatever value we return, this x is going to be less than or equal to 0.5 because this thing is in fact, we can like make the circles and we can make these squares if we want to distinguish, but just even, I mean, it's pretty obvious. We only have 3 levels, not like so many alternative things. So like, even if we get like 1, and even if we get like 0.99, and like we get like, even if we get like very good values, like we get like something like, even if you get like over 9,000 for good measure, like no matter what, like this minimizing player, even if it expands everything out and like get really promising values from P1, it's never going to take these moves because it's always going to give you like 0.5, or if anything like 0.3, or like negative 9,001, obviously. So it's like, no matter what it's going to return, it's definitely like again, like the best it's assured of, it's at least assured of 0.5. So like it can only do that or less. So like that's what it's going to return. And when you compare x and 1 for the maximizing player, well, 1 is going to be greater than whatever this thing can return. Like 1 is greater than 0.5, which is greater than or equal to x. Therefore, 1 is greater than or equal to x, transitive property of inequalities. So we don't even have to bother like considering any of these, because when we're kind of taking this, like whatever result that we get here, like this alpha basically comes from there. It's like, you know what, like my maximizing player, the alpha, is like it can like it's a like it can do 1, and we have seen 0.5 and we're minimizing. So it's like whatever route that this move 2 is, this route is never going to be taken because this player can always take this one and get at least 1. So he has 1 in his back pocket. So why would he ever do this and explore something that kind of gives him, he can only do worse? So it makes no sense to like all these future recursions can just be like swept away. So that's basically the essence of alpha beta. So that's the core idea. In fact, now let's go back to Negamax, because I believe like they had like, there's a base algorithm, but like if you go down, like we'll see AlphaBeta printing, and that's it. So actually, okay, let's actually kind of extract this initial call. I think that's a good like first order of business. So let's kind of do that and import that, obviously. So let's, sorry, I keep doing this. Sorry about that. Yeah, okay. So let's actually kind of keep this contract the same, but kind of return a new one. And let's call this like AlphaBeta helper. And then kind of like that. Like you have a whole class of like DFS algorithms where like the main function like DFS, and then like the actual like the outer function, it maybe does like builds a graph or does something, and then like it kind of passes it on to the actual recursive DFS helper function. See that pattern a lot in leak code tree questions. So again, like I'm still keeping the signature the exact same, and this one won't be exported, so that like we don't break our contract with BumperCoins. Again, we're still going to take in a game state and a depth, and like this is the function that we're going to actually return. So like we're kind of like doing that, right? So we're just going to call this return. In fact, we can delete this depth parameter because it is going to be passed into us from BumperCoins. Return from the consumer. Return the helper of the game state, the depth, and the negative infinity, and then for alpha, and then positive infinity for beta. And negative infinity first. To change the signature, I know. Just like that. Okay, so let's actually look at this code, right? I actually have to use the restroom. I'll be right back. Sorry about that. Right. I'll bring some water too, so I'll be back in a while. Yep, I'm back with some s'mores from Blaze Pizza that I'll actually quickly eat. But no, actually, as I eat that, actually, no, I'm gonna eat this because I want to enjoy it and then go over. Actually, no, I'll do them both together. Okay, I mean, for now, I'll just kind of eat this and contemplate this function as I eat it. Ordering, okay. A neural net policy network could help with the ordering because we can order it like with the highest probability first. Because again, alpha beta, we want to like kind of look at the most promising lines first, ideally, so that like when we're actually like doing the like we saw one, like the better cutoff we get, like because like 0.5 is like less than 1, and it's even more less than 9001, right? So like if this were like the higher this number is, the easier it is for stuff to be less than it. So therefore, like you will kind of truncate more and more. So yeah, I know like there's like I think like there's transposition tables, history tables. Like there's certain like kind of heuristics and like kind of techniques. Like you can reuse previous searches, move orderings to inform like because like what's good in one position, like in like you see this in chess, like what's good in like certain like openings, like whatever, like certain lines, like what's good in like one position, like in one like game state at like SFT could also be good in SFT plus one or something, like different move order, but like there's some generally kind of useful moves that you make in certain openings. Even if the move order is not exact, like it's still like same ideas, right? Anyways, yeah. Okay, I'll just accept this for now and move on. Okay. I wish there was a way to pause this animation. No, I can just keep refreshing it. Forget it. But I do want some concrete examples. Okay, sorry about that. I'm done. Child nodes, order them, then so what this is going to return, this whole thing right here, will be like the negation, so it'll be back to our perspective, the player whose turn it is, like the nodes, like the color whose turn it is. And then what we do is we set alpha. So alpha is basically the, like it says, the lower and upper bounds. So like alpha right now is clearly like the lower, like it's like yeah, like alpha and beta represent the lower and upper bounds for child node values at a given tree depth, right? So like initially like negative infinity, super low, and then positive infinity. So that's like our window, right? So then like we basically like alpha is like what the current player whose color it is. It's the best that they're assured to return something at least greater than alpha, right? And we keep maxing that. So that's alpha. So alpha is pretty well known. It's just like it's the best that we're assured. Like we know we can do at least this much. So like it's the lower bound because we can only do better. Like we're not going to return something. It's yeah. So that's alpha. Now if alpha is greater than beta, then we break. So like in this case, like in my thing, like the whole point was that like the whole point here is that like if alpha is greater than beta. I mean, okay, yeah, sure, we can do that. We can also do values greater than beta, right? Like, there's no need for a. Yeah, if the value is greater than beta, like, why are we kind of like, like the moment that this statement becomes true is when we break, right? So there's no point even like this line could be actually like. Anyways, that's just a trivial thing. I mean, yeah, alpha does that, sure. So like the moment that we are greater than beta, we break. So beta must mean like that like so what so like beta so let's kind of like look at the like this whole switching. I see there's negatives and I see that the flip order too. In fact, remember when we saw like the negamax how like the like this whole like A and B negative A? I think like that's the point of the switch. Maybe. I was like, why are you swapping the orders too? Because it's a commutative whatever, A, B, B, A, same thing. So it's like, so let's kind of like look at this. So like alpha, like what is beta in our like our child, our like in our recursion, in the next function we invoke. So what is beta? So beta for this iteration, for this execution of negamax, the beta term is negative of alpha. So first of all, negative basically flips the coloring. So like alpha right here is basically like what we are assured of. We can only do better. And then in this call here, the beta becomes what our parents, so like negative flips it from our perspective. So then this beta term becomes like what our parents, what are the other player, our opponent. So beta like is like kind of comes from alpha. So like in negative brings it back to our dimension. So beta is what our opponent can do. It is what our opponents can force basically. By playing optimally, it can force a certain score. So if our score is better than the score that it can force, that our opponent can force, then our opponent is never going to actually play into those, is actually never going to even reach us. Like, it's a moot point because, like, same kind of logic we saw there. Like, this node will never be hit because beta, our opponents, because, like, the value that we're going to do is going to be at least alpha, right? Like, we're going to return at least alpha. That's our lower bound, right? Alpha and beta represent lower bound. So, like, we're going to return at least alpha, but then our opponents could already force beta. So, yeah, so beta is the upper bound. So that's why beta is called the upper bound because, like, it's what our opponent can force. So, like, if our opponent can force a certain score already, and, like, and then like, it's already assured of a certain score, and, like, we can, like, kind of, like, why would it ever, like, entertain the possibility of even hitting our node and, like, exploring our node, expanding it further? Because like, from their perspective, it's really stupid to, like, to even, like, to play into our line where we get at least alpha because it can do better already. So that's why, like, the alpha and beta are flipped from, and then also negative signs is because it's negamax. Like, it's just to kind of, yeah, okay. So I think I kind of understand, like, yeah, like, it makes sense to me, this whole pruning stuff. So let's just kind of go ahead and just implement it then. Should be really straightforward. So our recursive call, basically what we want to do is we want to kind of pass in the -1 times beta, and then just like that, and then the actual pruning, right? So for max value, instead of max value, we will call this like just alpha. So child game state value is this thing right here, the child game state, and then the depth -1, the depth -1, and then we swap. We do like -1 times beta, -1 times alpha, and then the whole color is baked into the game state because the ESP1 turn gets toggled when we do apply move, right? And then we kind of negate it. And then if we're kind of better, like, because we're already assured of alpha, so like if we're kind of doing that, then the best move becomes this one, becomes the move that we found, which is not alpha, this is alpha, sorry. So if we've kind of found something that's even better, like if we found something that, well, it's at least, like, let's pretend that it's greater than strictly. So then if it is kind of greater, like if we found something that's quite good, that's like at least as good as our current best, then we set our record note in our best move because we're going to return it. And then but if what we get, but then like the alpha beta cutoff, so then like if the alpha is greater than the beta, so if alpha is greater than or equal to beta, we just break and we just return that. So we don't want to return max value, we want to return alpha, right? Or we return value. Wait, why are we returning value? Why aren't we returning alpha? Or maxing the value here. Oh, okay, yeah, no. That's perfectly fine. That is perfectly fine. Yeah, because these values could be really shitty and like our alpha doesn't even have to change. Okay, sorry about that. Okay, good. So we're here, right? So if the child game state is greater than that, then yeah, this is the value. So that's just like this stuff right here. And we kind of adjust alpha too for like future descendants. I wish these animations could be paused. Maybe they can, I don't know, but you know. So for all the moves, we we're iterating over all the moves, so then we get the child. The value from our perspective is -1 times recursive, noting to swap the betas and alphas. So again, like alpha is our lower bound, and then beta is our upper bound, as our article says, and we're assured of at least alpha. So then like let's say that like we're assured of at least 5 points. Then like from our opponent's perspective, their beta becomes -5. So from their perspective, like it doesn't make sense like doing anything that's better than -5, because like if they see like -4 or like 70 or something, which are both greater than -5, then whatever they're going to return, because like this negamax is a maximizing thing, the mins become maxes, like whatever it's going to return will be I mean, it's already greater than -5, so it's going to return x where x is greater than -5, but then the other player who it's going to return to, like they, again, can already force, like if they return like some x is greater than -5, let's just say -4, because -4 is greater than -5, and like they end up returning like -4, for example, then when you return it and then you flip and like you kind of negate it, because -4 is 4 from our perspective, from the callee, like I mean sorry, the caller's perspective, then like that caller has already like kind of has an like a already has an alpha of has the alpha of 5. So it sees a 4 and it's like, no, I'm not going to take the path that gives me a 4. I already have a 5 in my pocket, right? In my back pocket. So I can, like, I don't even need to consider any nonsense like that. So that's kind of why we swap it. And then the -1, we just saw that in action, flipping the sign. So the signs work and the swaps work. And then beta, I'm assuming, is like the dual case, the symmetric case. So yeah, I mean, that's just, yeah, everything. Like this stuff is agnostic. So yeah. Okay, so that looks good. So then we kind of so at least like that kind of makes sense to me. And then alpha, again, we're kind of always keeping track of like this window. We're just trying to contract this window we have here. So alpha, we kind of just max that. And then you might say like, hey, why aren't we minting the beta? But like again, the beta becomes the alpha. They interswitch. So it's like, yeah. So alpha is greater than beta, then yeah, we just talked. So yeah, so if the alpha is greater than or equal to beta, so then, like, whatever we're gonna return, like the moment, like we're already assured of something that's like from the other person's perspective, it's like we're never gonna like let us even get this far because they already can do better. So it's kind of like that reasoning. So alpha is greater than or equal to beta, then we just kind of return. We just break and then we break out of the for loop, and that just returns the whatever we like. We break and return. Like we don't care about the results because we're never gonna use them. So yeah. That's it. Okay, so I believe I've adapted it. Seems reasonable. Initially, like what we can do is negative infinity, because like that's like we can only do better. Like that's like the endpoint. Like that makes sense. Like that's our initial alpha. That's our lower bound. And again, beta is our upper bound because like positive infinity is from our opponent's perspective negative infinity. So like they're assured of negative infinity. And like from our perspective, it's just positive infinity. So yeah, so that makes sense. So I think this looks good. I think we're kind of done alpha beta. We just have this to do. Let's check if it compiles quickly. Great, it compiles. Get status. Get add all. Get status. Get log. Clear. Get commit. I'm just gonna save put this initial skeleton, or yeah, just initial skeleton of alpha beta bot, because again we have to fill in the to-dos, do the to-dos, but yeah, initial skeleton of alpha beta bot status. Okay, on branch temp. Why am I on branch temp? Oh, whatever. Okay, so main is here. Some training, temp, latest, initial skeleton of alphabet. Okay, so I mean, yeah, it compiles. So then I think that might be all for now, because like we've basically done a bunch of alpha beta stuff. Like we kind of have stuff. All we need now, in theory, is this heuristic function, like a bunch of like hard-coded features and weights. And then we need to generate the moves, but we can use like we have code from our like we can kind of copy, like we know like the number of directions is 8. Like we can consider like the north move, north, like the 0 to 7, like the 8 cardinal directions, north, west, south, east, northeast, and so forth. all the 45-degree pi over 4 increments. And then from those moves, we can like generate them as 0.4 intensity, just like we do in MCTS in net.2. So we just have to like kind of copy code from there. We could reuse it, but I think I'm just gonna be safe and just copy it because I don't want to break any existing code because we've already used that for training for many hours. So yeah, that's basically it. So we just have to do the to-dos and their AlphaBeta should be done. Okay, good talk. I'm going to I'm gonna stop now. I guess that's all for now. Just later on we have to do the to-dos, and then AlphaBeta, at least some initial version will be done. Of course, we can fine-tune the heuristic too to make it better, and like maybe we can do a hybrid approach where like we both combine different approaches, like hand code certain cases, like FSM or something, and then for other cases, just kind of use different searches. I don't know. Like certain things are like, hey, like if our opponent's king coin's on the verge of defeat, let's just kill it. And if we're about to die, let's just run our king away. Like some baseline, like greedy logic we can just kind of maybe do ourselves. But